Now we will see memory segmentation. Now, basically when a processor is interfaced with a memory, then there are two methods by which we can interface a memory with processor. One method is linear memory. And second method is segmented memory. Now in case of linear memory, whole physical memory is considered as a single memory, right? So continuously you can place your data or code or stack related data anywhere in the memory. Whereas in case of segmented memory, the physical memory is divided in logical parts, various logical parts, which is called as chunks, right? Various chunks of the memory. So we will see this segmented memory. Linear memory, in case of 8085 microprocessor, the memory interface was linear memory, right? So this for this example is 8085 microprocessor. Now, for the segmented memory, this is the concept of 8086 processor, right? 8086 processor. So, in 8086 processor, it supports the segmented memory concept. Now, this is our physical memory. Right? This is our, suppose this is 1 megabyte physical memory, right? Now this 16 MB physical memory can be divided in various segments, and there can be maximum 16 segments, right? So there can be maximum 16 segments, where each segment will be of 64 KB, right? In each segment we can 64 KB kilobyte memory can be a part of a segment, right? So maximum segment will be 16. Each segment of maximum 64 KB memory, right? So suppose there are total 16 segments and each segment is having 64 KB memory. So total how much memory will be there? So 64 KB multiplied by 16 segment. So this will give you 1 megabyte, right? So you can multiply it and find out the answer. So this 1 MB physical memory can be divided in 16 segments, and each segment will carry 64 KB memory. Now the segment address will be specified by segment registers, right? So segment address segment registers. So basically segment, now you just think, this is 1 MB physical memory. This is interfaced with 8086 processor. So if it is interfaced with 8086 processor, then 8086 processor will generate 20-bit address bits. So address bits are 20. So if processor will generate 20-bit address bits, so with those address bits we can access 1 megabyte memory. So suppose this is 1 MB memory, so this memory will have 20 address lines, right? From A0 to A90. So it will have 20 address lines. Okay? So processor will generate 20 address bits. But the internal architecture of processor is 16-bit. Means all the registers are of 16-bit. So, and if I say that segment register specify the starting address of a particular segment, but the starting address here, starting address of the physical memory will be 20-bit. Then how, but whereas the segment registers are 16-bit, so how that 20-bit address will be generated by 16-bit segment registers? So these things we will discuss, but right now you just understand that there can be 16 segments. For example, this is segment number 1, this is segment number 2, this is segment number 3, like this. Some more segment we will draw. Segment number 4, segment number 5, segment number 6, like this, segment number 16. Now here each segment can be of 64 KB. So this segment number 1 will be of 64 KB. This segment number 2 is also of 64 KB. Segment number 3 is also of 64 KB. Segment number 4, 64 KB. Segment number 5, 64 KB. Segment number 6, 64 KB. And segment number 16, 64 KB. So here there are 16 segments and each segment will be of 64 KB. So basically, physically the memory is same, but logically this is one segment, this is another segment, this is another segment. So what we are doing, logically we are dividing the memory in various small chunks, various small segments, right? Now here, suppose one processor is attached with this memory. In processor we are having 4 registers to specify the addresses of the segment. So these registers are code segment register, data segment register, stack segment register and extra segment register, right? So at a time, out of these 16 segments, we can active only 4 segments, right? So we can active only 4 segments because there are only 4 registers inside 8086 processor to specify the segments. So let us assume, suppose this is our code segment, this is our data segment, this is our stack segment and this is our extra segment, right? So out of 16 segments, we are using S3, S4, S5, S6. These 4 segments as our core segment, data segment, stack segment and extra segment, right? So what about remaining 12 segments? So those segments can be utilized by some other processor also, right? That's why the multi-processing concept is coming here, right? Suppose let us assume, suppose this is our memory, this is our resource memory, suppose RAM or ROM, and with this resource is shared by 4 systems. System number 1, computer number 2, computer number 3 and computer number 4. So here we are having, suppose this 1 megabyte memory. So suppose this, now what will happen? This computer number 1, it is having its own CS, DS, SS and ES registers. So with those registers, what it will do? It segment 1, 2, 3, 4. These 4 segments, right? Suppose what it will do? It use this segment 1 as code segment, segment 2 as data segment, 3 as stack segment, 4 is extra segment. These 4. Now segment number 5, 6, 7, 8. Now suppose these 4 segments are used by our computer number 2. Segment 5, computer number 2 is using as an extra segment, segment 6 as a stack segment, 7 is data segment and this is core segment. Now segment 9, 10, 11, 12, these 4 segments are suppose used by computer number 3. So he selected this segment 9 as core segment, 10 as data segment, 11 as extra segment, 12 as stack segment, right? And segment number 13, 14, 15, 16. These segments are suppose used by computer number 4, right? 13 as stack segment, 14 as data segment, 15 as core segment, 16 as extra segment. So now what is happening? This computer can active only 4 segments out of these 16 segments with the help of 4 registers: CS register, DS register, ES register and SS register. So suppose it has activated these 4 segments, 1, 2, 3, 4, right? Now computer number 2, it can also activate 4 segments. So computer number 2 activated segment number 5, 6, 7, 8 as extra segment, stack segment, data segment and core segment for its purpose. Now computer number 3, it can also activate 4 segment. So it activated segment number 9, 10, 11, 12. Same way computer number 4, it activated 13, 14, 15, 16. So now what is happening? This portion of the memory where segment 1, 2, 3, 4 is there, this portion of the memory is utilized by computer 1. This portion of the memory is utilized by computer 2. This portion of the memory is utilized by computer 3 and this portion of the memory is utilized by computer 4. So physical resource is same, physical memory is same, but this same physical memory is utilized by 4 different computers, 4 different processors, right? So this is the concept of multi-processing, right, or networking concept, which nowadays we are using, resource sharing, right? So it first introduced with 8086 processor. Now here one more thing. As I told you, each segment can be of 64 kb, right? So suppose segment 1 is 64 kb, 2 is 64 kb, 3 64 kb and 4 64 kb, right? So how much it is? 64 plus 64 is 128 plus this. Yeah. So this is 256 kb. So total 4 segment will make 256 kb, right? And these 4 segments of computer number 2, they will also make 256 kb. Computer number 3, 4 segments will also make 256 kb, and for computer number 4, the 4 segments will be 256 kb. So in total, if you calculate this, then it is 1024 kb, which is equal to 1 megabyte. Okay. So one thing is clear. Though we can connect 1 megabyte of memory with 8086 processor, but it can utilize only 256 kb of 1 megabyte processor or 1 megabyte memory. It cannot at a time use all the 1 megabyte memory. It can use only 256 kb memory with the help of with the help of 4 segments: code segment, data segment, stack segment and extra segment. But individually, one segment can use only 64 kb of memory, right? Now these 16 segments, the segment register will store the physical address is 20 bit, right? But segment register are 16 bit. And if segment register is used for the calculation of 20-bit physical address, then how it will bring the remaining 4 bits, right? Because physical address is 20-bit and segment address register is 16-bit. So what is the mean to add the remaining 16 bits so that it shall become the whole 20 bit, which can be considered as a physical address? So what happened in segment register? In segment register, higher 16 bits of 20 bit physical address will be stored, right? So higher 16 bits of 20 bit physical address will be stored in segment register, right? To calculate the starting of the segment address, for example, suppose these are the 16 bits, bit number 19, right, like this, bit number 0 to 15, right? Then 16, 17, 18, 19. These are 20 bits, right? Of the physical address. This is bit number, this is LSB, this significant bit, and this is MSB, most significant bit. Now, or is 15. Here it is 0, 1, 2, 3, right? 4 lakhs. Now, out of these 20 bits, which starts from bit number 0 to bit number 19, these are 20 bits, right? The lower 4 bits are bit number 0, 1, 2, 3. These are lower 4 bits. Right? We are talking about physical address. Physical address of segments, right? This is physical address of segment. So these are lower 4 bits, and from bit number 4 to bit number 19 are higher 16 bits. These are higher 16 bits. So higher 16 bits of physical address will be stored in segment registers, right? So higher 16 bits stored in segment registers. So now suppose our code segment register is having a value 1000H, right? This value we have loaded in, suppose code segment register 1000H. So this 100H is, in terms of bit, it is a 16-bit number. It is a 16-bit number. So for a physical address of 20 bit, from bit number 0 to bit number 19, these 16 bits belongs to higher 16 bits of physical address. So these 16 bits belongs to these higher 16 bits, right? These higher 16 bits belongs to this. But the physical address is 20 bit. Still we require lower 4 bits we require, because these are the 16 bit number, and these 16 bit belongs to higher 16 bit of a physical address, that is bit number 4 to bit number 19. What about bit number 3 to bit number 0, which belongs to lower 4 bit of physical address? So what bus interface unit will do? It will add, or it will shift this 16-bit number. It will shift the 16-bit number to the left side by 4 bits. Okay, how I will tell? So I will write this 1000H in bit format. So it is in binary. So number is 1000H. This is a hexadecimal number. So each digit reflect 4 binary numbers. So 1 means 0001 in binary. This 0 means 0000. This 0 0000, and this 0 0000. Okay. So what now our bus interface unit will do? It will shift, this is a 16-bit number, it will shift this number towards left side by 4 bits, by 4 locations, right? So now this 0 will come at new place, right, at at new place, that is this place. This 0 will come at this place. This 0 will come at this place. Like this, each bit will be shifted one bit left hand side. Right? So what will happen? You will get this 0, these 4 numbers. It starts from here now. 0, 0, 0, 1. Right? These 4 numbers will start from this position. This 0, 0, 0, 0. Right? This 0 is this. This 0 is this. This 0 is this. And this 0 is this. Now this position is bracket. So these 4 bits shifted left side. This 0 will come here. Then 0, 0, 0. Right? This 0 is here. This position is bracket. So 0, 0, 0, 0. In this way, the number is shifted left side. And here it is, one position is left. Right? When we shift the 16-bit number here, so at this bit position there is no number because this 0 is shifted here. So it will, bus interface unit will shift this 16-bit number left side by 1 bit, and whatever is the vacant position here, it will add one binary 0, it will add here, right? So in this way, this is first shift, right? Again it will shift, now this number, now this is a 17-bit number, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Now it will shift this 17 number again left side by another 1 bit position. So now what will happen? 0, 0, 0, 1. 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. And again this position is bracket because this 0 is this and this 0 is this. Now this position is vacant. Now again at this vacant position, BIU will add another binary 0. This is the second shift. Now it is 18-bit number. See, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Now again this 18-bit number will be shifted left side by 1 bit. So then it will become, this 0 will come here. This 0, 0, 0, 1. 0, 0, 0, 1. Then 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. This is this. And again here there is one vacant bit position. And again BIU will add another binary number here. This is the third shift basically. Now the number will become 19-bit number. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. So 4 times this 16-bit number, whatever is the value of CS register, it has to be shifted 4 times. So this is third time. Now fourth time again it will be shifted. So this 0 will again come at new bit position 0, 0, 0, 1 and 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. This 0 is this and this is a vacant position. Right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. This is the vacant position and BIU will insert another binary 0 at this position. Now 4 shifting has been done. Now what is this? This is a 20-bit number now. And this is your physical address, 20-bit physical address. Right? So in hexadecimal if we write, then this is binary 1, hexadecimal 1, this is 0, these 4 groups 0, these 4 groups 0, and these 4 groups 0. So it is 1, 0, 0, 0, 0. So this address, the physical address is 1, 0, 0, 0, 0. H. 1, 2, 3, 4, 5. There are 5 hexadecimal numbers because each hexadecimal number represents 4 bits. So 5 hexadecimal numbers are there. This means 5 into 4, there are 20 bits. So in this way, this is the physical address. So whatever is the content of segment registers, right? So those contents specify higher 16-bit of physical address of that particular segment, right? So basically what for the shortcut, what you do, whatever is the value of segment register, right? Suppose here it is, we take another case. Suppose our segment register is 3A40X. This is segment register, code segment value, code segment register value, right? This is a 16-bit number, is the value of code segment. And if we have to calculate the 20-bit physical address of our code segment, then simply in this, in 3A40, add another hexadecimal 0, right? That's all. This is your 20-bit physical address. Add simply one another hexadecimal 0. That's all, right? So now code segment register, this is code segment which is specified by CS register, right? And CS register contains higher 16 bits of starting physical address of our code segment, right? So see, in total there are 64 KB locations, right? Suppose this is first location of this segment and this is the last location of this segment, right? This is first location and this is last location of the segment. So what is the physical address of first location of code segment, right? That we have to calculate. That is required. So for that, what will happen? The code segment register will hold the higher 16 bits of physical address of starting address of the first location of code segment. Same way, this is our data segment. Data segment is also 64 KB. There is first location. So what is the physical address of first location of our data segment? So that will be specified by our data segment register. So again, data segment register is a 16-bit register. So data segment register will specify the higher 16-bit address, higher 16-bit of physical address of first location of data segment, right? Same way, this is a stack, this area is stack segment, right? This area is stack segment, which is 64 KB. So what is the starting location of our stack segment? So again, that will be calculated by stack segment register. And this is the extra segment. So what is the starting location of the extra segment? So that will be calculated by extra segment register. Okay. So now to find out the first location of the segment, the method is very simple. Suppose we want to find out the first location of code segment. Then whatever is the value of code segment register, in that you add 4 binary 0 at the LSB side, then you will get the starting location, right? You will get the starting location. But here now let us take one simple example. Suppose this is our memory. This is our 1 MB memory. Now in this 1 MB memory, let us assume this is our 64 KB memory area of data segment. Right, this is a 64 KB memory area of data segment. And data segment is specified by DS register. This is the first location of data segment, right? This is first location. This is second location, like this. This is last location. And last location will be 65,536, because in 64 KB there are, in 64K there are total 65,536 locations. Now the starting physical address of the data segment we can calculate, right? For example, if our data segment register is having a value, suppose 2000H, right? So what is the starting physical address of our data segment? So starting physical address will be, you add one more hexadecimal 0 at the right side, so it will be 20000H. This is a 20-bit physical address, right? So this is 20-bit starting location of data segment, right? 20-bit physical address, or okay, starting location of data segment. Now if I want to access this data segment, right, this location, this particular location, and this location is at the 10th position from the first location, right? From the first location, I want to access this memory location of this data segment, which is the 10 location apart from the first location. Then how to access this location? Right? We can calculate the data segment starting location with the help of data segment register. Right? Simply in data segment register, you add one hexadecimal 0, you will get the 20-bit physical address, which indicates the first location of the data segment. But if we want to access this particular memory location, which is 10 memory locations apart from the first location of the data segment, then how to access this? So this distance of the memory location from the first location of any segment is called as offset address, right? And the first memory location of any segment is called as base address, right? Base address. So what is base address? It is first memory location of any segment is called as base address. And whatever memory location you are accessing in a particular segment, from the base segment, how much far it is from the base address, that is called as offset address, right? So here, if this location is 10 location higher side from the base address, so this 10 is your offset address. This 10 is offset address. If you want to access the last location of this data segment, so the last location is at 65,536th position from the base address, right? So the offset address will be 65,536. So how much far is our memory location from the base address is called as offset address, and there are different means, various methods to represent the offset address. Okay, so there are different means to represent the offset address. So what are the various means to represent the offset address? That we will come to know when we will discuss about the addressing modes. Okay, so by now you just understand that in case of memory segmentation, total memory can be divided in 16 logical segments, whereas only 4 logical segments can be active for one particular processor, and those logical segments are code segment, data segment, extra segment and stack segments. Maximum memory location of any segment can be 64 KB. The benefit of this memory segmentation is we are having a 16-bit registers in 8086 processor, but we require a 20-bit physical address. So if to store a 20-bit physical address, basically we require a 20-bit register, but we are having only 16-bit register in the processor, right? So with the help of memory segmentation, we are able to generate a 20-bit physical address with the help of 16-bit registers. So this is the advantage of memory segmentation, that 20-bit address, physical address is generated by 16-bit register due to the memory segmentation. And due to the memory segmentation, it was possible to share the resource among the various processors, which is called as networking, right? And there is one more benefit of the memory segmentation. Whatever is our program code, we are able to now store our program code in code segment of the memory. The stack segment area of the memory is utilized for the stack purpose, for stack related instructions. The data segment and extra segment area of the memory is used to store our variables or our data, right? So we are having now different segments where we will store our different type of requirements in the memory. So in this way, these are the advantages of memory segmentation, and when we will discuss about the addressing mode, at that time we will discuss how exactly the physical address is calculated for different segments, right? But always remember, for the calculation of physical address, we require two things, right? We require base address and we require offset, right? And base address is calculated by CS, DS, ES and SS, these segment registers, and there are various means to specify the offset address, right? So this is, by this way we concluded this memory segmentation.